Welcome, everyone. Looking forward to getting this started. We have a presentation today for you on AC and DC coupling of batteries to solar systems. I'm joined today by my colleague, Daniel Moyer. Hi,
Hello,
Daniel.
Nathan.
Good morning.
Hi.
Welcome, everyone. Happy Thanksgiving. I appreciate you taking the time to join us. Again, today's presentation is on AC and DC coupling of PV systems with PHI batteries, simplified batteries, amplified batteries. It is a NABCEP certified training, so if you're here for those continuing education credits, please stay through the end. We'll ask you to email us. We'll check the attendance logs and issue your certificates. So please do stay through the end if you're here for the NABCEP credits. Those of you that are part of the IQ program, welcome. We're looking forward to talking to you a little bit about our IQ program in the end. So if you're an installer and you have not yet joined as an elite IQ installer, please consider doing so. We'll talk to you about how to do that at the end. We have a lot of content today. In particular, this training is going to focus on AC and DC coupling and how Briggs Stratton Energy Solutions produces products that can do both AC or DC coupled. The benefits of considering AC versus DC systems, especially in the case of retrofits where you already have an AC coupled array. And then talk about choosing the correct coupling based on your project configuration, etc. We'll get into the limitations of AC versus DC coupling as well. I want to highlight, as we do at the beginning of most of these webinars, that Briggs & Stratton acquired Simplified Power. And this was a couple of years ago now. We're now fully integrated as a complete integrated energy solutions provider. We make our batteries out here in California. We have been registered as a California manufacturer. So for those of you installing systems in California, that means an extra 20% discount on our batteries. And additionally, we're one of two providers that gives you both generator solutions, batteries, inverters. And so we offer a completely vertically integrated package for your ESS systems. It's one warranty call. It's one company to deal with. No blaming of other people's equipment when you're having an issue. And so it's a pleasure to be part of a company that has a complete solution like we do. So we encourage you to reach out to us. We are known for our customer support. I also want to point out that we have a number of free training opportunities. You obviously have found your way here to these webinars, but we additionally have the Briggs & Stratton Power Academy. That link is there in the upper left. We have in-person learning there as well, live virtual trainings there, e-learning courses, Power Academy Live, like I said, gives us an opportunity to do what we're doing now, host webinars, etc. But there's a lot of content on there that's learn at your own pace. So do check that out as well. And you'll likely receive some emails about the Power Academy. We're also now hosted on a new platform, and we're able to offer even more learning opportunities there. Additionally, we have upcoming trainings in December. Daniel and I are both delivering some new talks. We have an ESS and environmental considerations talk in early December that features our cold weather solutions that I'll mention just briefly today. I'll also be doing a talk about whole home backup featuring Solarc 15K with our batteries. And Daniel's going to be delivering a talk on off-grid living with simplified batteries, focusing on the off-grid market.
I'm looking forward to it, Nathan. Excited to do that right before Christmas. One thing that a lot of companies in this industry don't do is warranty and design their systems for off-grid. Simplified Power, Briggs & Stratton has found its roots in off-grid, and we're still supporting that market. Even though it may not be the biggest one, it's still an important one. Just chime in, we encourage questions during this talk. There's a Q&A chat at the top or the bottom. Please put your questions in. I'll kind of either answer them in the questions or I'll pitch them to Nathan during the talk.
Thanks, Daniel. Appreciate you bringing that up. Everybody, please do make use of the Q&A. It's our favorite part of doing these webinars, is getting to interact with many of you, and we often learn things as we're presenting material. What is an ESS? We're going to start out at the basics. In particular, we're going to be focusing on batteries and how they are coupled to solar. So ESS, of course, stands for an energy storage system. sometimes known as a battery energy storage system. But in the solar market, ESS, that means batteries connected to your solar. And today we're going to be focusing on how those connections are made, whether it's straight power coming from the solar array, which is DC power, or that power might be inverted with the use of microinverters or string inverters before it comes to the charging equipment and goes to the batteries. So that's what we'll be focusing on today, those two components. So as we get started, some key terms here. Many of you may be familiar with AC and DC coupling. If you are not, we're going to just define some basic terms. So coupling in the context of photovoltaic systems means how the solar panels are connected to the battery bank. So they have to be connected through a charge controller, but they might be connected through either an AC connection, means where the power coming out of the solar panels is first inverted and then sent to charging equipment. That's AC coupling. Or DC coupling, where you take that power directly from the solar array in the form of DC electricity, run that through some type of charge controller, whether it's a hybrid inverter or an independent charge controller, and use that to charge the batteries. Additionally, there's a term called AC coupled batteries, and AC coupled batteries are basically batteries that just have an inverter converter built into them to be able to export and import AC. You might have also heard of the term DC generators. There are generators that are coming to the market that produce DC power. And one of the reasons, as we'll get into, for wanting to feed DC straight to the batteries from different generating systems like solar or generators is to eliminate that extra inversion step, which can reduce efficiency. But typically, systems that are DC coupled can get higher overall efficiencies, typically around 92% or so round trip efficiency, versus AC coupled systems look at round trip efficiencies, which are lower, around 85%. However, there are other considerations to talk about, and we'll get into those. So DC coupling, let's look at the fundamentals of a DC coupled system. Typically, you're going to have power generation from a DC source, especially in most photovoltaic systems, right? You're starting off with DC power. I'll talk just a little bit about how that power is produced in a solar cell and then in solar modules. But there's some considerations to think about with solar arrays, and that is that there are different efficiencies and different impacts of things like shading. I can see in that solar array, there's a little bit of shading on that bottom left panel. And I can tell right now, looking up at the sun in the room that I'm in, that my solar array is getting blocked. One of my strings of my solar array is getting blocked by this branch of a neighbor's tree. And it has a very big impact on DC coupled systems. So we can talk a little bit about that, and we'll get into it. But that was one of the considerations you might have in choosing AC versus DC. So shading makes a big difference. There's string open circuit voltage, short circuit current, maximum power point, and maximum power point for current and voltage. So these are things we'll talk just briefly about today. We're not focused on them as much, as that's on the solar side. But temperatures do result in changes in the output of the solar array. Typically, solar arrays produce more power in cold conditions, but of course, typically in wintertime, colder conditions, the angle of the sun changes as well, and that can have impacts too. Charge controllers are equipment that use DC inputs to be able to supply batteries for charging. And some systems have charge controllers built into them, in the case of hybrid inverters. But we're going to talk a little bit about historical equipment as well. And we don't want to leave that off-grid community behind either, because it's often a lot cheaper to go with those older components or with those smaller components for off-grid systems. We'll talk a little bit about optimizing power source production as well. So how is power created in a solar cell? A solar cell is essentially a device that absorbs sunlight. That sunlight comes in, and inside the semiconductors of a solar cell, you have a transparent top layer, and it's got a different chemical doping in the silicon. And so basically what happens is when the sunlight is absorbed, it excites an electron, and that electron is accelerated through a built-in electric field in that solar cell due to something called the depletion region. But essentially, a solar panel is just an electron pump. It pumps electrons from the n-doped, from the p-doped side down to the n-doped side and creates a voltage, a little over half a volt, 0.6 volts or so for a solar cell. If you take many of those solar cells and put them in series, you get up to the voltages that you're used to for modules, 40-volt modules, 24-volt modules, etc. A solar system consists of many modules, often strung together, and you can see an example of a solar array there on the right, a solar system. The output of a solar panel is unlike a battery. It is not, sorry, I'm having a bit of trouble with my video, I guess. A solar cell is not like a battery module in that it just outputs a constant voltage. The current of a solar panel influences the output voltage, and typically we're following along an IV curve. The area under that curve would be the amount of power that you are producing. So you're trying to trace that IV curve in a way that you produce the most amount of power from that cell. And that IV curve changes with temperature. It increases the open circuit voltage with temperature, and the short circuit current can go up as well. And then higher temperatures lead to lower voltages and if affect the current too. So we're going to talk just a little bit about charge controller equipment. This equipment, it's designed to stay at that maximum power point of the solar modules of that solar array. There's different types of charge controllers. They all do basically the same thing, try to sit on the knee of that IV curve, producing the most amount possible. The charge controllers regulate typically fairly high voltage DC, especially with most home systems, you're looking at hundreds of volts. My solar array on my roof is bringing about 460 volts down to my Briggs Stratton hybrid inverter, which has two MPPT charge controllers built in, but there are different types. There's MPPT, maximum power point tracking charge controllers, and then there's PWM controllers, and I'm only showing one on the right side of the screen. So that one in the top left corner is very economical. It's $15 or so on Amazon. It's a pulse width modulation charge controller. Quite low quality, I imagine, but it's very cheap way to get power output out of a solar panel. I'll show you a better version of one in a minute, one that Daniel has. The other equipment there's a Midnight, there's a Morning Star. The Victron equipment as well has got that smart Bluetooth capability built into this. And these MPPTs can take about 99% of the power output out of your solar array and use that to charge batteries. They're highly efficient. You, of course, lose some power in the equipment. About 1% of it is turned to heat, hence the fans and the cooling fins on this equipment. But additionally, the battery itself has an internal resistance, which produces some heat, and you lose some energy there. But still, round-trip efficiencies, you can get as high as 92, 94% for good DC-coupled equipment. How does a PWM charge controller work? So as I mentioned, you have a higher voltage power coming out of your solar arrays. PWM controllers, that stands for pulse width modulation. What they do is they interrupt that high voltage signal with a series of FETs to produce a short-lived pulse. And this is typically occurring many, many times in a second. And so by pulsing that high voltage on and off, you get an average voltage, right, which is reduced, and that reduced voltage can be used to simulate 12 volts if you're charging a 12-volt type battery, etc. Daniel, you have one of those Sun Savers, right?
Yeah, and what's interesting about the one that you selected there, this is not only a charge controller, but it also incorporates a low voltage disconnect. You can see the load there. So DC loads, we're going to talk about that in our off-grid talk coming up, but DC loads aren't as popular as they used to be, but absolutely, it's a great, solid piece of equipment for Morningstar here.
Daniel, what's the price point on something like that?
I think we're a little north of 100, right in there, and they have a 10 amp version. You've selected the 20 amp version here that we're looking at.
I'm showing an MPPT charge controller here. This is a Midnight Solar charge controller. And again, what the MPPT is designed to do is increase the current, right, which causes the voltage of the output voltage of the panel to drop, or the array to drop if you're doing multiple panels. And by increasing and decreasing that current, changing that voltage, we're able to track the maximum power point of the panel. So if I started out in the top left corner, just short out my solar panel, I'm actually, even though I'm getting a lot of current out of the solar panel, I'm getting zero power, right? Because power is the product of current times voltage. So if I start to decrease my current just a little bit and increase the resistance, my voltage goes up and up and up, but eventually I get to a point called the knee of the curve. And this knee on an IV curve is where the product of current times voltage is maximum. And what you can see is power is plotted here as well on this blue line. And if I take the product of current times voltage everywhere on this red curve, I would have the area under my curve, or the size of the rectangle I could draw. And that increases until I get to this part on the knee, which is called the maximum power point. If I decrease my current further and increase my voltage, I get a drop off in power, and that is exemplified here. So eventually, if I decrease my current all the way down to zero, I'm back to zero power again, because even though I have the most voltage my panels put out, open circuit voltage, I have no current being drawn. And so what these MPPTs are doing is constantly stepping forward and backward to stay on that knee. Again, the IV curve changes with the amount of sunlight that's available. It changes with the temperature of the panels. It changes as the wind blows by, etc. And so these MPPTs are just constantly trying to stay at that maximum power point by making slight little changes up and down. And so that's what they're doing. One of the things that you can do is also incorporate things like DC optimizers. So if you have shading on a few of your panels instead of all of your panels, it can eliminate those panels and still keep a higher IV curve so that you're actually drawing power, getting the most amount out of your array as possible. Typically on the back of every solar panel, you will see ratings like are shown on the left. The maximum power point is called out at 350 watts on this particular panel. It's a polycrystalline panel, 156 by 156 cells, 38.5 volts, short circuit current of 9 amps. The open circuit voltage on this panel, if you were to be drawing zero current and just taking the multimeter and checking it, would be around 46.9 volts. That will change based on the temperature of the panel. Typically, you'll get a little bit less as that temperature gets hotter. You can also short circuit a panel. So a lot of people are nervous to short the positive and negative side of a panel together, but you should actually do that and test to make sure that you're getting somewhere around the short circuit current of your panel. You're not going to harm anything in the panel by shorting it out. It's just going to produce its maximum amount of current. And if you have a DC amp clamp, you can check that current when you're checking your solar panel. How do you land this equipment on the battery bus bar in order to distribute it to the batteries? So it is important that batteries stay balanced. And because of this, when we're landing, we're bringing power in through the solar panel. It's coming through, in this case, as a Victron smart solar charge controller. And that's going to be powering a bus in which all the batteries are connected to. It's important to use cables of equal length here. We want to make sure that we don't lose voltage. Anytime you're drawing or pushing large amounts of current through a cable, battery cabling, you lose a little bit of voltage, right? That small amount of voltage over time can cause different loads on individual batteries. And so it's important we use equal cable lengths and keep those batteries balanced. That way, one battery is not stressed more than the others or charged more than the others. This power out of the solar or out of the battery bank is then pulled in through an inverter and can go out to grid or can go to power the loads. It's important to use a single battery bank, even if you have multiple paralleled inverters, etc. So keep that in mind as you're designing systems. Here's an example of a DC coupled ESS system. This one's featuring our Briggs Stratton 6 kilowatt inverter. We've only got one of them here. You can parallel these units. What you see here are the solar panels. This is DC power coming out of them. These are not microinverters. These are rapid shutdown devices. I believe these are AP Smart units. And this is a DC disconnect for the solar array. This is a rapid shutdown button. And so I have this DC power coming out of my solar panels when solar is available, coming into a hybrid inverter. So it's a nice aspect of a hybrid inverter is it's got the charge controllers built in. The Briggs Stratton inverter has 2 of those built in. That power is then directed into the batteries. And once those batteries are full, or once we're in a time of use period where we want to discharge those batteries can be discharged to loads. If there's additional power in addition to what is charging the batteries available, that power from the solar is then directed to the loads as well. And if the loads are fully met and the batteries are charged and you have additional power available, can be fed back out to the grid. Another nice thing about this hybrid inverter is that it does have the ability to integrate a generator into a system. And this is especially important for off-grid customers where you might get some cloudy days, not have that solar available, but still want to be able to charge those batteries so that you can use them at night. The Briggs Stratton inverter has the capability through a 2-wire start signal to control the generator. So if the batteries get low on charge, it'll start up the generator. The generator will run, supply loads, and charge the batteries. When the batteries are charged up to the disconnect voltage or the redischarge voltage of that's set in the inverter, the batteries will then power loads and turn off the generator. So in an off-grid situation, this can be very useful, or in prolonged outages, it can be a useful way to be able to charge your batteries when solar is not available. This does not, of course, have to be a larger system. This could even be a plug-in with a manual on-off switch. You can bring that into the inverter as well. There's a 40-amp gen port on the Briggs Stratton inverter. AC coupling. Let's get into AC coupling. I'm showing here a Fronius inverter, which is connected to Victron equipment here. We've got a Simplify battery bank underneath. Power is inverted before being used to charge the batteries. So what's coming into that charging equipment is actually AC, and the charging equipment is responsible for converting that back to DC because charging the batteries, of course, requires a DC power cycle or power supply to be able to charge up those batteries. It's important to consider the PV arrangement. So with AC coupled solar systems, you have to consider where that power is coming from and going to. In the case of this equipment, there are some limitations as well. And if you are connected to the grid in a grid down situation, you have to make sure that your equipment is capable of frequency shifting and turning off those micro inverters so that you're not so that they're not trying to overpower equipment. Batteries are charged through the internal charger of the BB. There stands for battery bank inverter. This charger converts the AC to the DC to run those charge cycles on the batteries. You can also use a generator for AC coupling.
So Nathan, let's go back one slide. I want to make sure we're all kind of understanding why would we even do AC couple? As somebody who's coming from the old off-grid days, DC coupling always made sense, right? You lose efficiency, you lose something every time you switch from AC to DC. So taking DC out of the panels, DC into the batteries, and only when we need to power loads do we switch it. What I imagine in this picture here, and I don't know the exact details, but I imagine at some point they only had that grid-tied Fronius sitting there. And if we know, based on the anti-islanding rules, that if power went out, that Fronius is automatically going to shut itself off. So what we've done here is we've come into an existing site, and there's many, many sites out there that have existing grid-tied inverters. Now people want backup. So what the concept here is that we can now come in, add a battery-based inverter, and if the grid goes down, that battery-based inverter is going to continue to create a grid in the home. And as far as that Fronius is concerned, it sees grid and it's going to keep doing its thing. So why we AC couple here is the concept is we can come back to our existing customers, right? Go back, reach out to your existing customers that you've already done work for, offer them that battery backup solution. and get them that microgrid in their home. So it used to be, I had no understand why would we ever do this, but the reason is we don't touch the Fronius, we don't even get the ladder off of the truck. We just simply AC couple that existing solar into our inverter.
That's a great point, Daniel, and thank you for going into more detail and clarifying why you want to use AC coupled, right? And the other reason for AC coupled systems is there historically has been a good agreement with the grid for AC coupled systems, right? So you install AC coupled solar, you send power out to the grid, you don't have batteries, right? And you get compensated for that. And Daniel's given a talk just recently. Daniel and I went through a talk on NEM 3.0, explaining how that incentive for selling back to the grid has essentially disappeared in California, meaning that now battery banks are almost essential with the new interconnection agreements. So the existence of many solar arrays are AC coupled. And there's the question, yeah, I was going to answer that, Daniel. Thank you. Somebody asked if those were simplified battery racks, but no, we don't make those racks. I like the fact that somebody had made some pretty nice looking custom racks there out of square tubular. So I thought I would feature that here. So what happens in a grid down situation? Daniel was explaining that in the last slide, right? In a grid down situation, the grid is no longer there, which means that Fronius will automatically shut itself off. That prevents the solar array that you have on your roof from providing power in a grid down situation. So even though you've got a power generation source with a grid tied system, you don't have backup power, right? You need those batteries to create a little microgrid, and that microgrid can allow the Fronius inverter to pull power back out of those solar panels that it's connected to. The microinverter, or sorry, Solar equipment, sorry, it was Victron equipment in that last slide, right? Mimics the grid. Well, what happens if there's nowhere for that power coming out of the Fronius to go, right? Those battery banks are charged, the loads are met. We need something to tell that string inverter, right, to stop producing so much power, curtail the power, throttle it back. And what the way that you do that is you need equipment that's capable of frequency shifting. So the Victron equipment there will shift the frequency output of its signal when the grid is down, right, to curtail the output power of either microinverters or string inverters in the case of the previous example. And so that's 1741 SA. You need to make sure that your equipment has those capabilities if you are going to be AC coupling to it. So again, to curtail the power, we can shift that frequency up above that 60 hertz that is being expected, and that will slow down the output. That'll cause curtailment from the string or the microinverters. So here's an example of an AC coupled system. You've got solar panels. Those microinverters that are shown there on the screen are mounted right on the back side of those solar panels, and 240 volts AC is being fed through two lines back down to a loads panel. That loads panel is then coupled in. There's a shutoff there. Typically, there's a little bit more equipment. There's some communication equipment that goes with those end-phase microinverters. And then you'll be feeding through a fused disconnect. So I'm not showing it on the screen, but you need to have a disconnect for that micro array before bringing it back into the loads panel. Well, this type of system exists on many roofs. And as Daniel said, right, these customers want batteries as well, but we don't need to get up there on the roof and tear all those microinverters off. We can add batteries to the system. And Daniel, I believe we can add batteries to the system and even preserve that NEM 2.0 or NEM 1.0 status, right?
Yes, absolutely. And for those of you not in California, there's been some big changes in California. We went from a net energy metering structure where a one-to-one kind of kilowatt hour to a net billing tariff where we're selling at a different rate than what we're buying at.
And it's a much different rate to the point where it doesn't really make sense. You're getting pennies on the dollar to send those kilowatt hours that you generate back out to the grid. So it does make sense now to add batteries. So here's an example.
The last thing you want to do is go out to a customer and switch around things and file an interconnection agreement and get them kicked off that more favorable rate, which they're grandfathered into.
Right. So what we can do is we can preserve, at least in California, that older grandfathered in NEM 2.0 status, but still add batteries to an existing system. So what you see here is a retrofit where we've gone back in and AC coupled that power output out of those microinverters into a solar. And there are a couple of ways to do this. You could do this through the loads port, or you can do this through the gen port on the solar. If you do it through the loads port, unfortunately, you don't have the ability to monitor that AC coupled solar. So what I'm showing you on the bottom left of the screen is the output of a real system. I pulled this off of one of our customers' system output earlier this morning. And that's what you'll see. So you can see the microinverter here from the Solarc is producing a couple of thousand watts this morning. There's battery power as well. And this is an animated picture, so it doesn't really make sense as a still, but you can see the flow of that power. If you come in through the loads port, right, on the inverter, then you would be directing some of that power from the solar array directly into loads, so you don't have monitoring capability through the Solarc, but those end-phase units come with monitoring as well. You just don't have everything in one place as you do if you come through the gen port. Additionally, if you come through the loads port, it changes your timing on your battery backup. So if you're coming in through the loads port, it does take a couple of extra seconds. So it goes from an instantaneous, almost instantaneous 10 millisecond switchover to 2 seconds because those microinverters are there. And it takes a little bit longer to get everything back up. So keep those things in mind. You can, and Solarc recommends not going with a fully AC coupled system if you're designing a system. A mixture or DC coupled solar is always better. Applications, DC coupling. So if you're off grid, certainly DC coupling makes the most sense. You don't have a grid there to feed back to. So understanding what settings need to be made for your off-grid system is important. You'll want to know our float settings. What is our float voltage, Daniel, for our batteries?
54 volts.
54.0 volts, and our bulk setting on our batteries is 56 volts. So in a DC coupled system, you run a charge cycle, and that charge cycle, well, anytime you're using batteries, you're running a charge cycle. That charge cycle consists of 3 parts: a bulk cycle, which we push constant current into the batteries. Our batteries are rated at C/2. So if you have for example, 75 amp hour battery, you're going to be charging that at half that rate, 37.5 amps. And so you'll charge at a constant current, right, until you reach the bulk voltage, which is, in our case, 56.0 volts, right? Then it'll go into an absorb cycle where you just hold 56 volts for 6 minutes, and then we'll float those batteries if excess solar is available at 54 volts while that excess solar is being used to power loads. Battery backup situations, a lot of customers are wanting to just not lose power when that grid goes down. Maybe you have an important, it's important to you to stay connected. In my case, I don't want to lose power if the grid goes down, right? I want to make sure that my internet stays there. And so it's important to be able to have that battery backup for those reasons. Other customers want to be able to keep that solar going when the grid goes down. You can now use PV to charge during a grid outage with your DC coupled system. And of course, you get grid tied features such as cell through time of use. Time of use gives you the ability to control when you use the power that's generated from your solar array and stored in your batteries. You can also do something called peak load shaving by measuring and monitoring how much power you're pulling from the grid. And if you pull beyond a certain amount, the CTs that are detecting that will be integrated into your equipment, and you can use the software of the equipment to shave off those peaks. So peak load shaving prevents you from drawing too high of a power load from the grid.
Nathan, let's go back one.
Questions coming in?
Yeah, absolutely. Just as you were saying that, so there's been a couple of questions we've answered in the chat, but I got a good one that let's go ahead and answer this one live. Why are your battery systems configured for 48 volts? Wouldn't it be more efficient to use much higher battery voltages, not requiring a boost stage in your inverter?
Absolutely. So the reason is safety, right? So for large large scale systems, we do have high voltage offerings. We make batteries up to 1200 volts for our commercial and industrial purposes. But at 48 volts is effectively the standard voltage for home batteries, and it has to do with safety. Daniel, do you have more comments on that?
I would mention that some of the offerings by Solar 30K and the 60K can get higher voltages, but those in battery enclosures prevent user access to some of those high voltage bus bars.
Yeah, the other thing to point out with those is that 30K by Solarc is a 208 three-phase system. You've got 480 for the 60K, and we do have battery offerings for those if you are interested, again, in commercial and industrial. But for typical home systems where you're looking at two-phase or split-phase power, it's almost always 48-volt systems, and that's due to safety, and those safety considerations are built into the regulations. How about AC coupling of systems? So AC coupling, there are a lot of similar, right, types of ways that you would want to use AC coupled systems. Again, if you've already got an existing PV array, you'll want to be able to have battery backup for that array, and you would use an AC coupled system in that instance. So what we're calling a retrofit. So the array is already there, it's already AC coupled. We want to go in and add battery backup, but we don't want to have to pull a permit to change the array, for example, or change an interconnection agreement, etc. And so those are good examples of using AC coupling. That array is already there. There are other things, other reasons why people prefer AC coupling as well. It does a little better in shaded conditions, right? So with a typical string of DC connected solar panels, shading one panel can affect that whole string. And that's something that I experienced. One way around that is with things called DC optimizers, which will isolate that panel out and prevent it from affecting the whole string. But AC panels, because they're just all combined in parallel, don't have that issue. It's important to keep in mind how you AC couple can influence what you're trying to do. You might want to AC couple through the loads port of an inverter. So this is pulled out of a Solarc manual. If you also want to integrate other equipment, for instance. If you do want to use the gen port, you would need a transfer switch on your generator in order to be able to use both AC coupling and generator port. That's the same on our inverter. If you want to AC couple in solar, you can absolutely do that. We can take up to 40 amps on the Briggs Stratton inverter. But again, you would need a transfer switch if you want to integrate a generator. Some people will use manual transfer switches and just a plug-in portable generator, which is a lower cost option as well. Here's an example where we're actually looking at, that's a Solarc 15K on the wall, Briggs & Stratton 4.9 kilowatt hour batteries, 4.98 kilowatt hour batteries there. They've got 4 of them powering that Solarc 15K. That does have about 8 kilowatts of AC coupled solar coming from a N-phase array on the roof. We're bringing that in through the gen port there. Existing PV and AC coupling, so there are considerations that you want to think about. Challenges with DC coupling for existing PV systems. You have islanding mode and you have island mode. What does that mean, Daniel? What are we looking at with island mode?
You're an island in a sea of darkness.
So the grid goes down, right? You are now producing power. You do not want to feed that back up onto the grid, right? And so you want to make sure that your equipment is islanded from the grid. You are disconnected from the grid during an outage. And those hybrid inverters have the ability to create a little microgrid, right? And keep that AC system alive. So the example here where we have this Solarc, if that grid goes down, those batteries can power loads, but not only that, that inversion, that creation of the microgrid, the island, right, keeps those AC coupled panels alive and allows them to charge those batteries up and power loads during the day, even in a grid down situation. There are a lot of misconceptions of DC coupled systems as well. And some of these are even in the case of what I was just talking about. Many of these panels do have bypass diodes built into them. And with the newer split cell panels, Daniel, what's a split cell panel and why does that do better in shading conditions?
We've also heard them called half-cut cells, and it's very popular on the market now. Essentially, you have more cells in series, and that's boosting the voltage, and it's allowing you to have more bypass diodes.
So half of the panel would have cells on the top, more cells, right? And then the other half of that panel would have them on the bottom. And those two halves of the panel would then be connected in parallel to each other. So essentially, if the bottom half is shaded, the top half of that panel can keep producing. There are efficiency considerations. As I mentioned, AC panels do a little bit better in the sun. But again, you're losing that power even when there is no shading condition by inverting it and then changing it back, converting it back to DC for charging. So you have some efficiency considerations there. But if there is a lot of shading issues, AC coupled solar can also do better. If you have rooftop solar, it's important that you be able to shut off the solar array on the roof. Imagine there's a fire in the house and there's sunlight out there, and those panels, you've got a couple of wires hanging down through the roof, melted off vinyl that's covering them. Essentially, you have exposed wires that could injure firefighters. And so to be able to shut systems off at the module level, we need what are called rapid shutdown devices. And what the rapid shutdown device does is it allows the panel to be shut off at the level. Essentially, it's a relay, and that relay is receiving a keep alive signal from the inverter. And a rapid shutdown button allows us to shut off the panel at the panel level by turning off that keep alive signal. So the regulations differ from jurisdiction to jurisdiction, but I believe it's a nationwide regulation that all panels, roof mount panels, have to have a rapid shutdown device. So you can get module level shutdown through either DC optimizers, so they have that built in, or just rapid shutdown devices like Tigo devices or the AP Smart devices. And our inverter has a built-in AP Smart transmitter which sends that keep alive signal out. For AC coupled systems, as soon as that microinverter or that string inverter loses sight of a signal coming from the grid, those modules are made to shut down. So the microinverters will shut down as soon as it doesn't see a signal anymore. And so you just need a disconnect on those. Typically, those are fused disconnects. So there's a fuse inside that disconnect that you see there. So for a rapid shutdown device, here's an example where you can see a rapid shutdown button built into a DC connected system. These are optimizers here on the solar array. That's coming through a disconnect. But this device here is responsible for transmitting that signal. And that's the transmitter of the keep alive signal. As long as this inverter, as long as this button, this rapid shutdown button is in the normally open position, the inverter will keep powering that keep alive signal coming from the transmitter. And if you push the rapid shutdown button, what ends up happening is it kills the keep alive signal. Killing that keep alive signal turns these optimizers off and turns the panels off at the panel level.
Nathan, there was a good comment.
Sure.
You know, there is some exceptions for rapid shutdown on rooftop systems. For example, if the building in use is only used for solar equipment, or a carport type of facility. So there is some ways around that. Again, using some of those optimizers, you not only get the optimization, but the rapid shutdown built in. So thank you, Matthew, for chiming in on us.
Yeah, I appreciate that. Like I said, we always learn something from the questions as well. Here's an example for an AC coupled system. So we've got these N-phase microinverters. They're coming through their disconnect. And if we switch off that AC disconnect here, that will shut down the microinverters and de-energize the lines that are running out of that solar array into this Schneider system. Daniel, could you talk us through the 120% rule? So this is something that relates to how much power you are allowed to feed from your solar array, and it could be AC or DC coupled, into your main loads panel. And keep in mind that if you have power coming through the utility, typically that's running through a main breaker, right? Let's suppose that you had that main breaker and you're pulling close to 200 amps from that main breaker. Well, you can have power flowing through that main breaker, but also be contributing power from a solar system.
Exactly.
In that case, right, you could overrun the bus bars. Can you take us through this?
Yeah. So what we're looking at here is a DC coupled system. On the left, we have 2 strings of 8 LG 350 solar panels modules, and we're feeding them into the charge controllers built into that SolArc 8K, kind of sitting on the left-hand side there. We have 4 of our 5 3.8 batteries feeding into the battery input on that. We have a critical load sub panel there out of the load out port. But notice how we have the grid port. Now, the grid port is a 50 amp output, and we're feeding 50 amps onto a backfed breaker onto our main electrical panel. So when we went out to this house, essentially in the top right corner, we have a little chart. It says if we have a 200 amp panel with a 200 amp bus, the maximum that we could theoretically backfeed is 40 amps. Well, I just said that the SolArc 8K there has a 50 amp backfed breaker. So we could do one of 2 things in this situation. One, we could derate the main to 175 amp main breaker, or in our case, what we did, go ahead and click. What we did, oh, sorry, go back. I'm sorry. There you go. We upgraded the panel. We took the panel out. It was an old Zinsco, old GE panel anyway, so it needed to be upgraded. We went ahead and put in a 225 amp bus. So the 120% rule allows us to backfeed the panel up to 120% of the bus bar rating. So in this example, 225 times 1.2, we could actually have gone up to 70 amps. And the point being here is in worst case scenario, you have all of the loads on in the house, you have 200 amps coming in from grid, and we got 50 amps coming in from the backfed solar. We could theoretically exceed the bus bar rating of that main panel, and we could start a fire. We could melt the bus bar. So we're allowed to backfeed a little bit. And there's 3 kind of scenarios that allow us to do this. This is kind of demonstrating the 120% rule. Mayfield Renewables has some great trainings. I encourage everybody to check that out. There's a link to his source here. This is kind of the first way, and this isn't very common. What we're looking at here is we have a 1,000 amp bus, and this could be a 100 amp bus, right? It's just kind of an illustration here. But we have a main service panel, 1,000 amp bus. We have 800 amps kind of coming in from grid, right? So we kind of derated that main service. We have 200 amps coming in from our solar side. If you do it this way, it's not very common to do it this way, but it has been done. You can land that 200 amp backfed breaker anywhere in that panel, and you're good to go. Next slide. This is much more common. This is what we see a lot in the industry now. And this is saying that we still have that 200 amp, we have a 200 amp bus, and we have a 200 amp main breaker that's not called out there. And what this is saying is basically when you have 2 sources of power and you can locate that backfed breaker on the opposite end of the bus bar, you can have it to where the output current of that device should not exceed 120% of the ampacity of that bus bar. So essentially what you do is you're allowed to kind of exceed the ampacity of the bus bar as long as you locate that backfed breaker at the opposite end of where the main is coming from. And a lot of times there are center fed mains on panels. We're not going to get into that, but the idea here is that if you sending power in from one end of the panel and from the opposite end, it's not going to create a hot spot, or it's going to first supply power to any loads that are on in the home at that moment before, say, being backfed. So this is, you got to put a sticker on there. You got to sticker it up. This is another way to do it. And we've done this. You see these a lot in those IQ combiner boxes for Enphase. Essentially what this means is that you got an 800 amp bus bar on a panel. And as long as the sum of all of the amp ratings of those overcurrent of those breakers, both load and supply devices, don't exceed the ampacity of that bus bar, you're okay. So I can backfeed as much power as I want, as long as I don't, the sum of those backfed breakers and the sum of any loads that are in the panel don't exceed that 800 amps there. So one thing you do, again, you have to put a sticker on there saying, you know, this is being fed by multiple sources, and essentially don't add anything in this panel if you're going to exceed the bus bar rating. And so this is common and to do with usually inverter combiners as well, or so if you have. So the idea here is that if there's power coming in, it's power flowing out, as long as you don't have any loads for it to kind of make that worst case scenario.
Thank you, Daniel. I appreciate you taking us through that. So it's important, as you're considering your size of your strings as well, not to exceed the power limitations of your equipment. And that, of course, makes sense, but there's also some considerations as to when the grid goes down, how your battery is coupled to your system, and making sure that you don't exceed the power capability of your battery to take power in from that AC coupled grid. So you do want to make sure, if you're doing a DC coupled design, that you're limiting the amps through the charge controllers to make sure that you're not sending more power into the batteries than they can handle. Batteries can only be charged so fast. Our batteries are rated at C/2, which means that they shouldn't be charged faster than a 2-hour cycle starting from 0 and going to 100%. So that you want to make sure that you're using equipment where you can limit those amps to the appropriate size for your battery bank. It's also important to consider your wiring runs and making sure you're using cabling of equal length. And then there are limitations for grid down as well. And if you do have equipment like our inverter, you'll want to put a critical loads panel in there, so you're not trying to pull 200 amps out of inverter that's only capable of 40, right? So you'll want to make sure that you're paying attention to this and adding a critical loads panel. An example where you wouldn't need a critical loads panel is if you're using a larger inverter like a SolarArc 15K. You just have to keep in mind that SolarArc 15K is only capable of powering 15 kilowatts of load by combining battery and solar, and only 12 kilowatts when you're just going straight from battery. So there's some limitations on the equipment. Of course, you can parallel multiple inverters. You can parallel our inverter to double that 6 kilowatts to 12. You can parallel the SolarArcs to get more power out. For AC coupled systems, you'll want to make sure that you can limit the current through the inverter's internal charging system. And that's what I was talking about with frequency shifting earlier. Make sure that in a grid down situation, that your inverter is capable of frequency shifting and appropriately regulating the power output of those microinverters, not to exceed what can be consumed by your island. There are also some design considerations for commercial and industrial. And so again, if you are interested in high voltage systems, if you're interested in containerized solutions, we offer 3-phase power options with our commercial and industrial segment. We have a team of people that can help you work on designs, etc. Typically, you're looking at larger PV systems, and you'll want to incorporate optimizers and rapid shutdown compliance if you're going on a roof. Having DC to DC equipment like the Aztec inverters or the SolarArc 30 and 60Ks can help increase your overall efficiency. When AC coupled arrays already exist, it can make sense to use large scale battery bank inverters on AC coupled systems as well. There are some limitations, of course, and as was mentioned earlier, it's best, if possible, if doing a new design, to use a mixture of both AC and DC coupled solar. If you're using AC coupled solar with generators, it's important that you understand the capabilities of the transfer switches as well. And you'll need to make sure that the inverter is capable of taking both of those in. Daniel, I believe you have some slides on generators, and keep in mind that we've just released some new generators as well. Briggs Stratton is one of 2 companies in the US that produces both inverters, batteries, and generators. Daniel, can you talk to us a little bit about the Power Protect lineup we're looking at here?
Yeah, really excited to quickly run us through this as we're wrapping up the hour. Thank you everyone for being with us. A lot of times when you go out and you say, I want a 22K generator, a 22 kilowatt generator, if you look carefully at the spec sheet, that 22K generator is actually rated on propane. And as soon as you go to run that same 22K generator on natural gas, it derates. We have now introduced NG Max, which means that our generators do not derate whether you run them on propane or natural gas. And what's exciting about that is also we can offer these generators for off-grid use. A lot of these standby generators are not warranted for off-grid use. We have a nice lineup there of residential style generators. Additionally, we do have some liquid cool commercial generators as well.
Thank you. The batteries that we offer come in 24 and 48 volts. The PHI battery is one that we've really got a lot of history with and is typically used in off-grid markets. That does come in a 24 volt option. It comes in a 48 volt option as well. The communicating batteries that we have here that you're looking at, the Amplify, the wall hung outdoor rated Simplify 4.98, those batteries are only coming in 48 volt nominal sizes. So it's important to consider that. There are limitations for the communicating batteries as to how many of them you can put in parallel. You only put our batteries in parallel, never in series, right? So you would never take two 24 volt batteries and try to power 48 volt equipment with it. It would lead to imbalances and loss of warranty and eventually loss of functionality in that battery. So keep that in mind. These are a great lineup of batteries that the Amplify battery, if you're doing an indoor install, you get a little bit more bang from your buck. It's not a waterproof battery, but for an indoor installation, that battery offers complete communication, temperature control as well. And that Simplify battery is a wall hung battery. So we have enclosures that can give us some options for these batteries, the PHI and the Amplify battery, if you do want to install them outdoors. This is our Boss 6 and our Boss 12. These are our Boss 6 and Boss 12 cabinets. These are UL 9540 certified, UL 9540A safety tested, and they're NEMA 3R rated. So if you want to install them outdoors, you need to have these little rain hoods on the temperature regulated fan in that cabinet. But these are rated for outdoor install, so you can install the PHI, the Amplify battery outside, but you would just want to do it in one of these enclosures. These enclosures can hold a very large overall capacity in terms of getting 12 of those Amplify batteries or 12 of those PHI batteries in the enclosure. Additionally, one of the things that we've done with these enclosures is also offer them with as a complete ESS system. We've got our hybrid inverter that's featured here. Earlier, you saw the Solarc featured inside these cabinets. We call these our access cabinets. It's basically a plug and play solution. Comes pre-programmed. You have to mount the batteries, make the connections, and essentially the system is ready to go. It's a fully integrated system. Again, it's UL 9540 certified, and it can come with up to 137 kilowatt hours for this Boss 12 enclosure. We can also put multiple access cabinets together to produce 208 three-phase power if you need it. If you're installing in cold environments and you're installing outdoors, you might also be interested in having some temperature control. So we have a somewhat unique heating pad design that is actually built in the factory. This is a special order item, but if you know you're going to be installing batteries in a cold environment, you might want to order them with these heating pads. These heating pads are temperature controlled, and so if the battery temperature gets below freezing, temperatures below freezing are dangerous for lithium batteries, especially in the charge cycle. These heating pads will come on, draw a little bit of power. I think it's 120 watts out of the battery to warm up those batteries, right? And then that charging cycle can commence without any damage to the batteries. So if you're interested in this type of solution, it's something that we offer. Daniel, can we do a quick check on questions?
Yeah, there's a great one. Why do we need a minimum quantity of 3.8 kilowatt hour batteries, 24 volts on inverters. What happens if we use only one battery, for example, on a 3,000 watt inverter?
So if you take your phone and you talk on it, or you're streaming videos for a long time, one of the things you'll notice is that phone gets hot, right? Batteries have an internal resistance, and when you're drawing large amounts of current, that current generates heat. So if you're trying to draw huge amounts of current out of a battery, that battery will start to get hot. And a hot battery can damage the electrolyte that's inside it, and cause degradation inside the battery. So there are output ratings on the batteries. Batteries are designed for different discharge and charge rates. You would never take one of these 24-volt batteries and hook it to a 24-volt vehicle and charge and run it through the starters, right? If you did that, you would damage the battery. Car batteries are designed for really high cold cranking amps. These batteries are designed to last a long time and to output power for numbers of hours, but not designed for huge amounts of power. So if you try to draw, so for instance, a 3.8 kilowatt hour battery, if you discharge all that 3.8 kilowatt hours over the course of 2 hours, that battery would produce 1.9 kilowatts continuously. They can surge for a short period of time, but if you did that for a long time and didn't meet that minimum requirement, you would damage the battery by producing too much heat inside it, etc. So there are power limitations on batteries, and that was a great question. Thank you for asking it.
Last question. So, why are we using an enclosed wiring tray or trough here? I think you might have been referring to this last slide. Go back one. No, forward one. I believe it's the one you were on.
Okay.
It really it's a way to keep those conductors safe and best practices for code.
Thank you, Daniel. Appreciate you answering that. This is a nice system, and it's actually installed in Alaska. So we get a lot of customers using our solutions in the cold environments in Alaska. I'm not sure who the installer on this particular system is, but you see a couple of solarcs that are paralleled there. You see combiners for those batteries. The nice thing about the Amplify and Simplify, we've designed a really high-end BMS that we make, and it offers the ability to curtail the power in cold environments. So these batteries can operate at a greater range of temperatures, and I thought I had the temperature slide in here to explain that, but they can operate at a greater range of temperature. They just reduce that charging rate. So these can operate all the way down to negative 20 degrees Celsius. It slows down the charging rate at those temperatures. But eventually, because of the increased internal resistance at low temperatures, charging those batteries slowly at low temperatures raises the battery temperature, and that allows us to charge faster. There's a pretty unique solution with these communicating batteries. The Briggs Stratton Energy Storage System can be both AC and DC coupled. It does come, so you can use it with our 4.98 kilowatt hour battery. You could also use it with the other battery offerings that we have. And one of the important things about inverters and energy storage systems is this software, right? The software can make a big difference. Well, we developed this Energy Track app in-house. We own the code, and we're constantly enhancing it to make it better and better. It gives you the ability for firmware updates, remote firmware updates, remote system monitoring, real-time monitoring. It gives you the ability to make remote configuration changes as well. You've got a customer that wants to do something different with their system, or maybe wants to increase the amount of battery reserve they're having due to inclement weather. You can do that from the office instead of having to go out and make a change on the physical system. So here's an example of a DC coupled Briggs & Stratton ESS. I am showing it here with a generator. Of course, that's optional. It's not necessary, but it's got that 2-wire start signal with a generator. DC coupled in that solar array is just passing through Keep Alive rapid shutdown devices. Those are AP Smarts there. You've got the disconnect, you've got the rapid shutdown button. So it's a nice example of a DC coupled ESS. Of course, you can parallel more inverters than just one. A single inverter will give you 6 kilowatts of continuous power. It's enough for my home, but for larger homes with air conditioners, you might want to parallel several units to get increased power output. Here's an example of a Briggs Stratton system that's using AC coupled solar coming in. And so this is an example where we have N phase. I am missing, I'm sorry for this, I'm missing the disconnect, the AC disconnect in this diagram. But we can bring that AC coupled solar in through the generator port. We can take in up to 40 amps through that generator port and connect that to the batteries. It's shown here, of course, with a critical loads panel. So if this grid does go down, the batteries can supply essentially an island, a little microgrid, which will allow these microinverters to come back on and charge the battery bank, power loads, etc. in a grid down situation. That's normally something for microinverters and AC coupled systems that you don't have. In a grid down situation, you don't have solar power. Well, add even a small battery bank and you can keep that solar power pumping. So here are a couple of examples. I think the one on the right and the one on the left, the one on the right actually is just a battery backup system. You don't have any solar feeding into it. It's connected just through the utility connection. And in the event that the grid goes down, this keeps an office building going. On the left side of the screen, you're looking at a DC coupled ESS system installed with one of our customers in Puerto Rico. And this system that's being built here is an example of a system with an AC coupled. There's 10 kilowatts of N phase there. It's AC coupled, but it's AC coupled through the loads panel. So it's actually running that power through utility. The downside to that is you don't get to monitor that power with Energy Track. But the upside is that you can couple larger AC arrays by doing it that way. I was asked earlier about higher voltage stuff. Isn't it more efficient? Lower overall requirements on wire size, etc. to go to high voltage? Absolutely it is. We make battery banks all the way up to 1200 volts. We have a full array of batteries for this need. We even have containerized solutions. In the county just south of me, Santa Barbara County, their whole government office buildings are being powered from containerized solutions over a high voltage battery. These come in 4.3 kilowatt hour banks, batteries, either 48 volt or 24 volt modules. Each of these has to incorporate a stack controller. And as I said, they can go up to 1200 volts for large scale solutions. So if you are not installing batteries, now is the time to do so. It's being estimated that in just the next few years, 1 out of 3 solar installs will include batteries. And with the changes in net energy metering here in California, there's now a huge incentive, if you're going to add solar, to have batteries and to self-consume that energy. Again, Energy Track makes a big difference. It's our monitoring platform. It allows us to be able to see where the power is going, and it offers a very fast commissioning. I can commission our inverter systems after they're set up in less than 10 minutes. It also allows fleet management, which means that you can see all of the inverters and the ESS systems that you've installed, and it allows remote configuration of commissioned systems so that you can make changes from a distance. These are some screenshots of what Energy Track software looks like as you're monitoring, showing you a real-time view of what's happening with the power, telling you information about the system, showing you what the batteries are doing, how much battery reserve you have, what firmware version you're running, etc. Through this app, you can enable things like time of use, which allows you to set the times when you want to discharge your batteries, maybe to prevent you from using energy from the grid when it's most expensive. So I'm on a time of use. I'm on a plan that gives me elevated rates during the evenings. And so using something like time of use can prevent me from using power from the grid when it's the most expensive. And again, this Energy Track gives you the opportunity to change settings remotely. So suppose you're away from home, you know there's a storm coming in, you want to have that power if the grid goes down. Well, you can change the battery reserve, for instance, on your batteries, just to keep that energy until you're home.
And I want to pause this here and say thank you, everyone. I know we're going a little bit over time here. So as we're wrapping up, I'd put any questions you might have here at the end, and we'll just, thanks for sticking with us, and we're almost done here, and we'll get you some questions answered here in a minute.
Yeah, I appreciate you staying around as well. So we have, I'll get done in just about 1 minute here. We've got a 15-year warranty on our communicating batteries, which this is a full 15-year warranty. We don't have any throughput limit on our batteries. It's an unlimited number of cycles. We guarantee that at the end of 15 years, you'll have at least 70% of your original capacity remaining in those batteries as well. If you are not part of our Elite Installer program, we encourage you to join it. Give us an email or give us a call, training@simplifypower.com. We'd like to get you on our map. We often recommend installers that are listed on our map. We also give you a quarterly $25 per battery that you install back as a cashback bonus. And there are a number of other benefits as well. I'll be sending these slides out to you. I do want to highlight that we've got some promotions running. We have a $1,000 rebate with a purchase of your first ESS system. So we're running that right now. We have a $75 rebate on every battery that you purchase as an authorized installer, and a $100 rebate on every battery purchase as an Elite IQ installer. So you get that extra $25, a $100 rebate for IQ installers. Also, with our 4.9 batteries, we're giving away a free conduit box with each battery that's being purchased through the end of the year. And if you buy 5 batteries and purchase a Boss 6 cabinet, you'll get that 6th battery completely free. So these are being run through the end of the year. I encourage you to take advantage of those. And for projects in California, again, we are listed as a California manufacturer by the CPUC, and you can get an additional 20% rebate through SGIP. You do have to apply for that, but you can get that money back from the state of California. So again, thank you for joining us today. Happy holidays. I hope you enjoy your Thanksgiving on Thursday. And if you're here for those NABCEP credits, just send an email to training@simplifypower.com.
Yeah, thank you, everyone. Thank you, Nathan, for a great presentation today on AC/DC coupling. Couple last-minute questions. Can we get a non-NABCEP certificate for our attendance? Yes, please email us at training@simplifypower.com. Let us know that's what you want. Last question, unless somebody else gets one in. Do these battery chemistries, I think they're referring to lithium iron phosphate, have any sort of hazardous off-gassing that should be addressed when they are installed inside of an occupied building? And so I think we should address, are they allowed to be installed in an occupied building? And then maybe address that a little, Nathan, and do they off-gas? I think it's two separate things there.
So first answer is no, they do not off-gas. These are hermetically sealed batteries. However, right, even though LFP batteries are about the safest battery you get. So first off, hermetically sealed just means that nothing comes in or out. In the event of a building fire, however, right, let's suppose that maybe a fire gets started in the garage. If the batteries heat up beyond a certain amount, they can off-gas. And in that case, you could have the potential of these vents opening up on the batteries to prevent them from exploding. In that case, there would be chemicals that would be hazardous to breathe in. And that's the case for any lithium battery, right? LFP batteries, I want to emphasize, are the most safe chemistry on the market. That's why Simplify has gone with them. That's why Briggs Stratton continues to encourage this battery for home use. But as Daniel just said, you cannot install these, so you can install them in a home, but you cannot install these in living spaces, right? So if you are going to install it, it has to be in an electrical room. There are NEC regulations around that. You need 5/8" drywall. You can install it in a garage. Some local municipalities have regulations around needing parking ballards or bullions. What do you call those, Daniel?
Bollards.
Bollards, parking bollards, etc., to prevent an accidental, car from running into a battery, etc. So great question. Let's end it there. Have a happy Thanksgiving, everyone. And if you're looking for the NABCEP credits, again, our email's on the screen. Thank you for your attendance. Enjoy your Thanksgiving.